morning, class. I think we can start. We are now 20. I believe others will join us along the way. So I hope you'll be able to finish the sulfonamides today. We've done most of the unit, we discussed most of the materials which are concerning the sulfonamides, but whatever we've left, I hope we'll be able to cover it this morning. So I think we were able to go up to this slide, if I'm not wrong, acidity of sulfonamides. So of course, we did mention the sulfonamides are very, very weak acids. And of course, their level of acidity is also highly influenced by the substitution at position number 1, that is at the nitrogen at position 1, and of course specifically on the sulfonyl group or on the sulfonamide group. So the group that you put there, it should be electron withdrawing. If it is electron withdrawing, then it will make the hydrogen more electron deficient and therefore allow for more ionization. Of course, we did say after the ionization occurs also, that most of those heteroatoms, which is either nitrogen, sulfur, or oxygen, also have lone pairs of electron. The sulfur has lone pairs of electrons, the oxygen has lone pair of electrons, and all these lone pair of electrons participate in stabilizing the anion through resonance. And the more stable the anion, the higher the acidity of that sulfonamide. Of course, the higher the acidity of that sulfonamide, the higher the solubility. The higher the solubility, as we are going to see, the lower the toxicity. So we are saying, looking at the acidity of the sulfonamides, and we are saying they are weak organic acids, and this, of course, is due to the sulfonamide group or the sulfonyl group. And this can be able, you see this sulfur, double bond O, NH2. So you find that because of the fact that, as you can see here, double bond O, S, double bond O, and the nitrogen is attached with sulfur, there is a pool. The oxygens are highly electronegative compared to sulfur and nitrogen. So they'll pull electrons away. And once they pull electrons away, this is where we are starting. Once these oxygens pull electrons away, you can lose one of these hydrogens. You can lose a proton from here. And once that happens, you establish the negative charge. And now the negative charge is what we are saying is stabilized through resonance. The electrons come in, the electrons move out, and this charge can move. This can come back here, and this goes out. So that is what we're calling stabilization by resonance. And we're saying the attachment of electron withdrawing groups onto N1. And this is what we are calling our N1. So once you attach electron withdrawing groups to this nitrogen, then you find that your drug is more readily ionized, is more acidic, and therefore it will not only be more potent, but it will also have lesser toxicity. So we're still discussing the same. Too big. So sulfonamide, or the sulfonamide group, or what we are also calling the sulfonyl group or the sulfonamide group, that is the SO2NH2, is unstable and gets stabilized by losing a proton, which results in negative charge being stabilized by resonance with sulfone group. So what we are saying is that you again the same thing we had discussed, that loses, you lose that proton and you have that negative charge, and it is being stabilized by using the sulfone group, and then that can come in, and if that comes in, all that means this also can go out. So we can extend that, whereby this can carry a negative charge, or even this other one can carry a negative charge. Therefore, the sulfonamide group can be considered as a weak HA acid, whereby, of course, the hydrogen is this hydrogen here, and the rest of the molecule is the A. That is the A. This is what is forming ion. So this molecule is what we are calling the A, and the hydrogen, of course, is what we have lost. HA acid, similar to other acids like the carboxylic acids, whereby you can call also this HA. The carboxylate ion is the H. The hydrogen, of course, is still the H. So the carboxylate ion, is the A, and that is the H-phenols, also benzene. Of course, that's a pheno and thios. The R group in the sulfonamide group, that is SO2NHR, affects the ionizability of the proton of the nitrogen proton. If R is electron withdrawing group, the antibacterial activity and solubility of the drug is improved. And we are giving an example that pyrimidine is more electron withdrawing than benzene and thiazole rings. Thiazole substitution produces toxic sulfonamide derivatives. So we are only giving an example, like where we have a pyrimidine moiety, where you have two nitrogens, that is, the two nitrogens are more electron withdrawing than a thiazole ring, a nitrogen and a sulfur. And therefore, when you have a thiazole ring, that sulfonamide can crystallize or can be deposited in the kidneys, and also it will have poorer water solubility and also lower activity. The lipid solubility influences the pharmacokinetic and antibacterial activity, and so increases the half-life and antibacterial activity. That is, of course, for all drugs. Once you have drugs that have good lipid solubility, they penetrate the membranes better, and therefore improve on the reach the minimum inhibitory concentrations, and therefore will, of course, improve on the activity of these drugs. Again, also high lipid solubility, that drug takes a bit longer to be metabolized. So when it gets into the body, it will not be eliminated the way it is. It must undergo metabolism, and that usually is what gives the drug slightly longer half-life than a drug that is highly water soluble. A drug that is highly water soluble will not require metabolism. A drug that is highly lipid soluble will require metabolism, and therefore a slightly longer half-life. The urea and pKa of the sulfonamides. And we are saying, despite the good ability to treat infections, this is the sulfonamides. Should be sulfonamides are associated with severe renal damage due to crystallization in the kidneys. Of course, or sulfanilamide. You can still say sulfanilamide is associated with severe renal damage due to crystallization in the kidneys. But I'm assuming because of the way they are saying, considering this should be sulfonamides. But sulfanilamide is, of course, the prototype of the sulfonamide. Very poor water solubility. Remember, sulfanilamide is not substituted at the R position. It is actually SO2NH2, just like the other side. So it is not substituted with any electron withdrawing group, and therefore very, very low ionization, very poor water solubility, and a lot of crystallization in the pKa of the sulfonamide group, that is the SO2NH of sulfanilamide, is 10.4. So you can see the pKa is very, very high. And the higher the pKa, of course, the lower the Ka. The lower the Ka this time, remember, now we are talking about acids. So if you have very low Ka, then the acid will be very weak. And the weaker the acid, if you have a very weak acid, and of course, we did mention the urine itself is acidic. Weak acids will be precipitated in acidic media. But if you have a weak acid media, you will increase the solubility of a weak acid in a basic media. You will decrease the solubility of a weak acid in acidic media. So therefore, we are saying, because this sulfanilamide is a very weak acid, when it gets into the urine at pH 6, then it will be precipitated. And once it will be precipitated, of course, we will get what we are calling crystalluria. The precipitated sulfanilamide in urine leads to crystalluria, and that is one the major side effect toxicity of the sulfonamides, and that is what you have to try and avoid when you give the sulfonamides. And you will see how we are able to alter. There are several ways we can alter. Of course, one through, as we have said, structural modification of the sulfonamide can give you sulfonamide with a lower pKa and a higher Ka, and therefore improved water solubility. Of course, the other way you can do you can reduce the crystalluria is by alkalinizing the urine. So sodium bicarbonate can also be administered before each dose of sulfanilamide to improve solubility and thus excretion in urine. And all we are saying is that because this is a weak acids are more soluble in basic media. So instead of the urine remaining acidic, you alkalinize the urine by giving sodium bicarbonate. And once you alkalinize the urine is basic, the sulfonamide is a weak acid, more soluble in basic media, and therefore better elimination, and you will avoid crystalluria. The other thing you can do is increase the water in fluid intake. Increase the fluid intake, so that now when you increase the fluid intake, then you give a bigger volume of fluid in which the sulfonamide or sulfanilamide can dissolve, and therefore also increase. And that is why when you dispense sulfonamides, you are supposed to advise your patients to take a lot of fluids, not necessarily water, to try and increase the intake of water. So the methods used to reduce the crystalluria of sulfonamide is one, increase urine flow to reduce the opportunity for crystals to seed in the kidney. And one of the ways to increase urine flow is to take a lot of fluids. So you take a lot of fluids, doesn't matter what, you increase the urine flow, and therefore you increase reduce opportunity for crystals to seed in the kidneys. Increase the pH, which we have already said. The closer the urine pH is to 10.4, of course 10.4 we have said is the pKa of please do remember that when the pH is equals to pKa, when pH is equals to pKa, then you find that your drug is 50% ionized. 50% ionized is good enough. And that's why we are saying we could make the pH to approach the pKa of sulfanilamide, which we have said is 10.4. And when the pH is equals to pKa from Henderson, I believe you did do chemistry again, we call it Henseberg-Henderson's equation. From that equation, you will see that when the pKa equals to, then whatever compound you have will be 50% ionized. Will be 50% ionized, and 50% ionized is good enough. And if that 50% ionized, the drug will not bring about crystalluria. So that's why we are saying increase the pH of the urine to approach the pKa of the drug. And once the pH of the urine approaches the pKa of the drug, by increasing the basicity of the urine, then the drug will be more ionized, and of course, it will eliminate crystalluria. Again, also the final one, which is very important to us, is preparing derivatives of sulfanilamide that have low pKa. Because the lower the pKa, the higher the Ka. And the higher the Ka, the higher the acidity. And a strong acid, a slightly stronger acid, will be ionized even in acidic media. If you have a strong acid, it will be more ionized even in acidic media. It is a weak, very weak acids. They are the ones that are very poorly ionized in acidic media. So therefore, increase the acidity of the sulfonamides by decreasing their pKa and therefore increasing their Ka and allowing them as close as possible to the urine pH. So this time what we are lowering the pKa. Remember the pKa of sulfanilamide is 10.4, very, very high. So you try to lower the pKa of these sulfonamides to approach the pH of urine. The pH of urine is 6. So you try to lower the pKa of sulfonamide from 10.4 to around 6. Once you do so, the drug again will be 50% ionized. And once it's 50% ionized, you will not have a problem of crystalluria. So you prepare derivatives of sulfanilamide that have low pKa as close as possible to the urine pH. Again, we are using the Henderson-Henseberg's equation to ensure part of the dose is ionized. That's about 50% of the dose is ionized in the kidney. The pKa can be lowered by using electron withdrawing groups at N1, as we have already discussed. Again, it's just to further emphasize on the same, and this is just what we have discussed. The strongly electron withdrawing, that's just the point where we ended. We have said that you put electron withdrawing groups, so we are continuing this. Sorry, this one is we are considering the SO2 first. Sorry, the strongly electron withdrawing character of the aromatic SO2 group makes the neighboring nitrogen atom to which it is directly attached partially electropositive, in turn increasing the acidity of the hydrogen atom. This is just what we have said, that once this sulfone group is electron withdrawing, and because it's electron withdrawing, it will first withdraw electrons from the atom that is directly attached to the sulfur, which is the nitrogen. The nitrogen becomes slightly electropositive instead of electronegative. important electron withdrawer, withdrawing electrons from the hydrogens, and one of the hydrogen is easily lost. And that is what explains the acidity of the sulfonamides or sulfanilamide. It is because of the sulfone group withdrawing electrons from the nitrogen, making it electropositive. In turn, it withdraws electrons from the neighboring hydrogen. The hydrogen becomes electron deficient, and therefore readily lost, and that gives us the acidity. So increasing attack the nitrogen and facilitating its removal as a proton, so that this functional group is slightly acidic. pKa 10.4. That is sulfanilamide. And then, of course, we did mention once a negative charge is formed, there is stabilization and there is movement of electrons, so that you have that negative and you can have that negative. And remember, stabilization by resonance brings a lot of stabilizes the anion. Once the anion is stable, that means the sulfonamide can stay ionized. Replacement of one of the hydrogens of the amino group by an electron withdrawing heteroaromatic ring was not only consistent with antimicrobial activity, but also greatly acidified the remaining hydrogen, whereby the hydrogen gets a pKa between 5 and 6 and dramatically increased potency. So you increase the acidity of the molecule. So when you put R cyclic ring, starting also with the thiazole ring, the pyrimidine ring, the isoxazole ring. So the only difference is the different rings will have different powers of electron withdrawal. The higher the electron withdrawing power of the heterocyclic ring, the more acidic the sulfonamide is, the higher its potency and the lower its toxicity. So that is the role of R. R helps to increase the acidity of the sulfonamide and also helps to increase the potency of the sulfonamide. So you can see that is our R we have lost. So you have here NHR, you have lost that proton. So this proton should not be there. It should be NR, because we've already lost that proton. So that proton, we have lost that proton. I don't know why they're repeating it here, and again, it shouldn't be there. We've already lost that proton, so that becomes a minus, and of course there is movement inside there, and then this already is stabilized, but this proton nevertheless should not be there, because if that proton is there, then what have we lost? They are treating it as if it's an NH2, so there's a mistake here. So the hydrogen has been lost, and therefore this is NR and not NHR. It's NR negative, and then the negative comes in, and once it comes in, then this goes out and goes there too. Then this can come in and that can come out, and that of course is the next one there. So that's what we are saying. Therefore, the R is a very important group because it increases both potency and also increases decreases the toxicity of the sulfonamide. And we are still on the same importance of substitution at R2, sulfonamide analogs with reduced toxicity. So it's just to give examples, you can understand what we're saying. When these drugs are metabolized, they are mainly metabolized through acetylation. So if you look at this drug, sulfathiazole, that is a drug, sulfathiazole, you can see that is a thiazole ring, sulfathiazole. So when it's metabolized, the amino group is acetylated in a reaction catalyzed by N-acetyl transferase. So if you find when it is acetylated, you can see there will be formation of the amide. And this amide has lower than the drug before metabolism. So the metabolite has much, much lower water solubility. So you can imagine if this drug itself, the sulfathiazole, has poor water solubility, the metabolite has even more poorer water solubility, which implies that metabolism of this drug will result in a metabolite itself. It has issues with this crystalluria, but the metabolite will even be worse. It will even intensify the toxicity. So how problem sorted out? This is the problem you're saying was sorted out by changing the heterocyclic ring. Like we have said, thiazole has poor water solubility. It's a weaker electron withdrawer. So you change that, you replace the thiazole with a pyrimidine ring. So you replace it with a pyrimidine ring to get sulfadiazine. And the two nitrogens have much higher electronegativity, much higher pool of electrons, and therefore you can see the pKa of sulfadiazine is 6.48, and it is approaching the pH of the urine. The pKa of sulfadiazine is 6.48, approaching the pH of urine, and therefore approaching 50% ionization. So this drug, you can mean approaching 50% ionization, when, of course, the pH of the urine is 6. Sometimes definitely it's not exactly 6. So they are saying when the pKa is 6.48, the drug is 86% ionized. The drug in the urine is 86% ionized. And once it's 86% ionized, then sulfadiazine will not have issues of crystallurgia. And sulfadiazine will also have better potency than sulfathiazole. So that is very important. So we are therefore saying substitution, replacement of the heterocyclic ring with a ring that has higher electron withdrawing effect, increasing the acidity and of course decreasing the pKa and increasing the acidity of the sulfonamide, gives us a better molecule with lesser toxicity and higher potency. Another drug is sulfamethoxazole. Sulfamethoxazole also slightly different, of course, different from sulfathiazole, but definitely if you look at sulfamethoxazole, I would expect sulfamethoxazole to even have a lower pKa than sulfathiazole, because oxygen, in this one you have nitrogen oxygen, in the other one you have nitrogen sulfur, and oxygen is a more potent electron withdrawer than sulfur. So this should have a much lower pKa compared to sulfathiazole. So that's sulfamethoxazole, and again, not rapidly absorbed as sulfamethoxazole. And so we compare it with sulfamethoxazole. So when you look at this, compare sulfamethoxazole, it has sulfamethoxazole and sulfamethoxazole. What are some of the differences that we note? We note that both of them have the isoxazole ring. Both of them have the isoxazole ring. But the main difference is that there is a reversal of the order of the nitrogen and oxygen. In sulfamethoxazole, you start with the nitrogen. It is the nitrogen that is attached, directly attached to the carbon, which is attached to the NH. In sulfoxazole, which I expect to have the very quite low pKa, you can see it's the oxygen, and the oxygen has a stronger pull. So the only difference here is the order of arrangement of these groups. Oxygen being more closer to the nitrogen, which is attached to the hydrogen, and therefore this oxygen exerting more pull of the electrons, and therefore giving this compound much lower pKa than, or much higher water solubility than the sulfamethoxazole. And that's why we are seeing not rapidly absorbed, because sulfamethoxazole will have also a slightly higher water solubility. And of course, when it has higher water solubility, it will go into solution rapidly, get the concentration, create a concentration gradient. It still has mercury, it still has good lipid solubility. So it still retains good lipid solubility, and then it acquires higher water solubility. Remember, its higher water solubility allows to undergo dissolution much faster than sulfamethoxazole. And when it undergoes dissolution much faster, it means it will give you the molecule that will be there. There will be a higher concentration of the molecule to be absorbed in the aqueous media, and of course there will be better passage through the lipid barrier. So the only difference here, of course, even this drug, you also realize that it has two methyl groups, and of course the methyl groups also will improve on its lipid solubility. But because of this oxygen being attached to the nitrogen, this oxygen is having a major influence on the polarity of this group drug, increasing its acidity, allowing it to be highly ionized, allowing it to be highly slightly more water soluble than sulfur methoxazole. Getting into solution, it still retains good lipid solubility because in place. In sulfur methoxazole, you have one methyl group. So here, so that you can balance on lipid solubility, you add another methyl. You have good water solubility. You improve on the lipid solubility by addition of another extra methyl group. So that drug has good lipid solubility. It has got good water solubility. So there is a balance of lipid water partition coefficient. It is well ionized and therefore minimal or no crystalluria. No need for using alkalinizing agent with it, and because it has very good water solubility. So this is what we were saying. So you can see that is a pyrimidine derivative. If you look at this drug, this is a drug we call sulfamethazine. We're going to look at them and we'll be able to see the difference between one and the other. So let's look at the various. So that this we've already looked at. Let's look at the various compounds. This we have already mentioned, so that is not new. We are only saying that this is the thiazole ring directly. This thiazole ring is directly attached to that nitrogen, and now we are saying in this the NH proton is not very acidic. That means it has therefore sulfur thiazole and its metabolite are mostly anionized at blood pH. Replacing the thiazole ring with a more electron withdrawing pyrimidine ring increases the acidity of the NH proton by stabilizing the resulting anion. So we are saying this group here is more electron withdrawing and therefore allows for more rapid formation or more stable formation or more stable anion. And once you have the more stable anion, then that much lower toxicity and much higher activity. Hence, sulfadiazine and its metabolite are significantly ionized at blood pH. As a consequence, they are more soluble and less toxic. Silver sulfur, that is a different thing. So we're only looking at pKa values of some ionizable sulfonamides, and you can see when you look at sulfadiazine, it has 6.5. Sulfamerazine, I think we need to look at the structures. So I think we come here. This is sulfanilamide. This is the one we started with, sulfanilamide, and it has 10.4. And of course, we say that's an NH2. That's an NH2. Then we have sulfathiazole, which has an 8.5. So you can see, because of introduction of the thiazole ring, there is a decrease in the pKa as expected. Then you have sulfoxazole, and sulfoxazole is where the nitrogen is the one which is attached past, and you can see sulfoxazole has, this is wrong. Keep making the wrong, giving us the wrong structures. Let us look at the structure of sulfoxazole. Sulfoxazole is where the oxygen is attached. So again, please note some of the structures that can be wrong. So sulfoxazole should be the other way around. If we are talking this is with sulfoxazole, we are talking about this oxygen, sorry, we should be here. There should be an interchange of that. So this structure, you know that structure. Sulfadiazine. So sulfadiazine, that's correct. You have those two nitrogens, and you can see again the pKa as compared to the pKa of sulfathiazole. pKa is a bit lower. Then you have sulfamethazine, and now you need to understand when you look at sulfadiazine and sulfamethazine, that's why I wanted us to look at those structures. They say I want us to look at that, and there is another one. Where do I have that other one here? I don't have it. I wanted the one with one methyl group. All right. Anyway, when we look at this structure here, this is sulfadiazine. It has a pKa of 6.5. If you look at sulfamethazine, which has 2 methyl groups, it still has a diazine ring. It still has a pyrimidine ring, but on it has substitution of 2 methyl groups. The 2 methyl groups, as we had said earlier, donate electrons through sigma bonds. And since they donate electrons through sigma bonds, you'd expect that the electron withdrawing power of these nitrogens is reduced because they're a little bit more satisfied by electron donation from the methyl groups. And therefore, you find the pKa of sulfamethazine is much, much higher than the pKa of sulfadiazine. The one with the 1 methyl would lie here in between. All we are saying is that when you substitute with alkyl groups, which are electron donors, then of course you will increase the pKa, and of course once you increase the pKa, of course you increase the toxicity and you reduce the reactivity. Then sulfacetamide, we did mention that this incidentally also has a very low, reasonably low pKa, and of course that is because of this carbonyl group, which is directly attached to the amino group, and you know that oxo group is directly an electron withdrawer. But we did mention that is mainly used for conjunctivitis. That is just used as an eye drop. Then you have sulfadoxine. And again, if you look at sulfadoxine, we can be able to understand. Again, it is similar, very, very similar. Of course, the nitrogens are they are arranged differently. The nitrogens are further, because it is still a pyrimidine ring, but with nitrogens placed farther away from the nitrogen. So the pull by these electrons, by this nitrogen, will be much lower than you'd expect in sulfadiazine, because of course this nitrogen is well placed, but the second nitrogen, you would have expected it to be in this position, but now it's further from the nitrogen than when you are considering sulfadiazine, so that decreases the pool of electrons, or the power, the electron withdrawing ability of the second nitrogen. Further to that, sulfadoxine has also methoxy group. Methoxy group will stabilize our electron donors, and therefore again that is why that drug has a much more higher pKa, because of the substituents, which are methoxy groups, are pushing electrons into the system the way the nitrogen is arranged. But do remember, we did mention that when you have these alkyl groups or the alkoxy groups, they help in the binding at the site, because we did mention that these do bind some of the enzymes like arginine, which are found in the site or at the receptor. And we did mention, of course, they will also influence, as we had mentioned earlier, they will also have a very big influence on the plasma protein binding. They will have an influence on the protein binding, and that is why a drug like sulfadoxine has a very long duration of action. Remember, we did mention metaplaced alkoxy group, metaplaced alkyl groups, metaplaced halides. Some of the proteins within some of the amino acids within the proteins, amino acids including arginine, and once they bind those amino acids, protein binding gives drugs longer duration of action. And of course, we also said they will also interfere in the binding of this drug at the site, and therefore giving us better activity. Sulfamethoxazole, this sulfamethoxazole, so this is where this is the sulfamethoxazole as we had seen it. Now, as I said, this we have to reverse it, oxygen, nitrogen there. So sulfamethoxazole, this again we had looked at, and you can see again the nitrogen and oxygen very, very close, nitrogen and oxygen. And in this order, if it's oxygen which came first, as in sulfoxazole, then the pKa would be quite low. But because it's the nitrogen that's attaching first, and then also you can have one methyl, the metamethyl increases the pKa, but you can see because nitrogen and oxygen being more electronegative than sulfur, this drug will have a much lower pKa than sulfathiazole. Then finally, we have sulfapyridine. Sulfopyridine has only one nitrogen. You can see that, and that is why its pKa is a little bit high. So when you look at these drugs, you can't be able, even by looking at the structures, you should be able to, even if you don't remember whether this one has 2, 4, 5, it's pKa, but you can't be able to compare and be able to say, would you expect drug A to have lower pKa than drug B? And you say why. You should be able to compare pKa's of different sulfonamides depending on the heterocyclic group that is attached, or depending on the group that is attached at nitrogen 1.